It's time to get started. First of all, welcome. And today we are really honored to have Professor Mike KOSTERLITZ to come to give us a talk. And I think for those of you who are doing physics, I guess Professor KOSTERLITZ doesn't need that much introduction. And he is a Nobel Prize winner in, I think, 2016 for his work on topological phase and topological phase transitions. And before that, he already had a lot of prizes, including the Maxwell Medal and also the Onsager Prize. And well, I'm just trying to do my homework to introduce Professor KOSTERLITZ. And then I found out that Professor KOSTERLITZ was not only a world-class scientist, he's also a world-class mountaineer. And he's very famous for rock climbing and so on. And there are, in fact, trails that are named after him. So maybe Professor KOSTERLITZ also tell us something about rock climbing later today. Now, but before I forgot, but I also have to recognize Dr. Suyu Chen and Professor Jiong Hang. And they were our physics alumni, and in fact, without their help, Professor KOSTERLITZ will not be able to come to this lecture. So it is actually their partial sponsorship that makes this talk possible. So this is Dr. Chen and Professor Hang there. And so without further ado, welcome, Professor KOSTERLITZ. Okay.
I'm very honored to be here speaking in front of this audience. And the title of my talk is Random Walk Through Physics to the Nobel Prize. Now, in this talk, I'm not going to go into much technical detail, but I will tell you some of the story about how I ended up in Stockholm on the 10th of December 2016, meeting the royal family and getting a Nobel Prize. You see, I even have proof that I was there. There's in the middle, there's Berit, my wife, and myself, and the Swedish royal family. There's the King of Sweden beside Berit and the Queen of Sweden beside me. And then the others are the various royal princesses and their husbands. At the time, I was a bit nervous because I had a very bad back and my balance had gone a bit. So I was a bit nervous about escorting the royal princess down the stone steps in the concert hall of the in Stockholm. But she said, look, don't worry about it. I'm a big girl. If you slip and fall, I'll catch you. So after that, we got on pretty well together. Now, I hope the story I'm going to tell you will encourage some of the students in the audience that good fortune can happen to anybody, no matter how dim your prospects may seem. So I thought I'd tell you some of the story about how I got to Stockholm. See, here are the three of us who shared the Nobel Prize. Now, when I found out about the Nobel Prize, of course, I was incredibly surprised and pleased about it. And then it turned out, I found out how the money was split between the three of us. And I thought, hey, wait a minute. There are three of us getting the prize, so surely it should be a third each. Why are Haldane and I getting a quarter each, and Thowell is getting a half? What's going on? So I thought about it for a bit and eventually figured out what was going on. Turned out that the prize was being awarded for two separate but related pieces of work. And there were two people involved in each piece of work. So in principle, that meant that there were 4 people that were a quarter each, but there was a small problem in that the maximum number of people who can be awarded a prize is 3. So but of course, everything worked out okay because two of the people involved in the two separate pieces of work was the same person, David Thowles, which explained why he got 2/4 of the prize and Haldane and I got 1/4 each. Actually, the Nobel Committee was a lot smarter than I was. Now, so I thought, now, let me go back to the beginning. I was born in Aberdeen, Scotland in 1943. My parents were German sort of refugees. My father, who is on the picture here, that's my father, the big one, and me, and I'm the small one. My father came from a non-practicing Jewish family, and my mother came from a right-wing Aryan family. My father worked at the Charité, it's a hospital in Berlin, but in 1932, he discovered that Hitler would allow him to work, but not to be paid. At this point, my father decided that things weren't too good for a Jewish person in Germany, so he used his contacts in Britain and looked for a job over there. He was offered various temporary jobs at several places, but Aberdeen University offered him a permanent job, which he accepted. Now, of course, there were two reasons why Aberdeen was very attractive. Firstly, the security of a permanent job, and there was a Nobel laureate called MacLeod, was in Aberdeen, and my father wanted to work with him. But unfortunately, MacLeod had the very bad grace to drop dead shortly after my father's arrival, so he had to make his own way. He worked there for about 60 years, finally quitting at age 90 when old age took over. Now, my mother, who came from a very right-wing Aryan family, followed my father from Germany to Scotland, and they got married in Glasgow in 1934 and settled in a small house in a village about 4 miles from the centre of Aberdeen, where I grew up. Now, I went to school in Aberdeen, a semi-private boys' school, where I received a pretty good education. I could give up the subjects I disliked when I was 16 and concentrate the ones I liked and was good at. Fortunately, my parents never overtly tried to influence my choice of study, but I naturally gravitated towards maths and science. I hated all the humanities, literature, languages, fine arts, etc., and I think this was because of my very poor memory. I like to say that I can remember a maximum of 10 facts, but I'm not too sure about the last 4. Now, all the humanities subjects, of course, are very memory intensive, languages, history, geography, literature, and I always struggled with these. Mathematics and the sciences, on the other hand, could be handled with a minimum of memory and an extensive use of logical deduction, which suited my way of functioning. My education was a bit torturous. Now, I went to school from age 4 to 16 at Robert Gordon's College in Aberdeen, and then my father decided that I might be good enough for Cambridge University, so I was sent to a school in Edinburgh for a couple of years, where the teaching went up to the English advanced and scholarship level as needed for the best English universities. Now, I got through this easily, again, getting top grades, and was accepted at Cambridge University with a prestigious bursary or scholarship to study natural sciences, which did not include any other subjects. Now, initially, I got a bit bored with the teaching because I'd learned almost all of it at my Edinburgh school. However, the chemistry was fun, but it got turned off by an incident where a test tube of a colourless fluid I was staring at started to change colour. I held it out at arm's length to the side, and then it exploded and sent shards of glass into my cheek. Now, to this day, I have no idea what happened, but it turned me off chemistry, big time. There were one or two other incidents during which I discovered that I'm red-green blind, which makes distinguishing test tubes with different shades of red rather difficult and sometimes dangerous. You can imagine what it's like trying to drive at night with the traffic lights. You know, hardly be able to distinguish green and red. Now, these difficulties, together with my poor memory, made me decide to go for the simpler but safer subject of physics. Now, my academic Cambridge career also got disrupted when I joined the Cambridge University Climbing Club, which ran a bus or a van every weekend to either North Wales or the Lake District or Derbyshire Gritstone. And I was introduced to the sport of rock climbing. And I found that I was, quite good at it and quickly became addicted to it. There's nothing that can compare with the rush one gets when you step out into the unknown high up on a steep cliff, knowing that a mistake could have serious consequences up to and including death. And this concentrates the mind to an amazing degree. And I got completely addicted to this adrenaline rush, if you wish. And the climbing became my main interest, followed by physics and my newly acquired Swedish girlfriend. Now, of course, not surprisingly, I didn't do as well as I hoped or was expected to, and in the final examinations, I sort of screwed up royally. So I did a fourth year at Cambridge, doing Part 3 mathematics, otherwise called applied maths, to try to rescue my academic career. But my climbing passion intervened again, and I didn't do as well as I'd hoped. I was turned down for graduate school in high energy physics theory at the Department of Mathematical and Theoretical Physics at Cambridge. Ironically, I was offered a place as a graduate student with Sir Neville Mott to do solid-state physics in the physics department, the field for which I later would win my Nobel Prize in 2016. However, I turned this down in favor of grad school in Oxford in high-energy theory, which at the time was the glamorous physics field. Now, in Oxford, I worked on what are called dual resonance models, otherwise called the Veneziano model. And these models, actually, I discovered later, were precursors to modern string theory, of which you may have heard. And managed to publish a couple of papers, which at the time were probably never read. Now, on completion of my DPhil, that's what Oxford calls a PhD, in 1969, I was awarded a 2-year Royal Society Fellowship, which I could use anywhere in Europe. So my girlfriend Berit and I, who's now my wife of over 50 years, and another Oxford graduate student went to Torino University as postdocs. Torino is, of course, in Italy. And I chose Torino because of the proximity to the mountains. But also the physics there was quite good in the persons of Sergio Fubini and Tullio Reggi. You've heard of Reggi poles, and Tullio Reggi is the guy who actually invented those. Now, the three of us rented and shared an apartment in Torino, in Italy, And this made the ladies in the local milk shop very, very curious, because you could never figure out which of the two males this Swedish girl belonged to. Neither, of course, she belonged to neither, but this was 1969 after all. Now, I had a wonderful year in Torino. My scholarship from the Royal Society was sufficiently generous that Berit and I could eat well and go skiing in Italy, France, and Switzerland every weekend, and the occasional week in the winter. Of course, it helped that I had climbing friends renting apartments in Verbier and Lausanne in Switzerland, and we could always sleep on the floor there for a couple of nights, so we rarely had to pay for hotel rooms. I also managed to continue with my rock climbing and did some climbs which weren't repeated for several years. I was introduced to the local young mountaineers from Fiat, the car factory, and it was a fun experience because they were very good climbers, but there was a problem because I, of course, didn't speak that much Italian, but they didn't speak or understand a word of English. Now, communication, as you may imagine, communication is vital when one depends on each other when hanging onto a steep cliff, sharing one rope. My Italian improved dramatically because, as you might understand, I became very motivated to learn it. Now, let me go to, there's a picture of me and two of my friends, climbing friends in the French Alps. Unfortunately, I am the guy on the right in the background. Unfortunately, the other two, well, the guy in the front, Mick Burke, died in Everest. And the other one, Martin Boyson, he's still living in Britain. Haven't seen him for years. Now, last February, sometime later, I returned to Torino to receive an honorary doctorate in physics, but discovered that in that region of the Alps, I'm better known as a climber than as a Nobel laureate. And in effect, I'm actually labeled as having introduced the so-called new morning of Italian climbing. Now, okay, let me tell you a bit of a story about when the winter of skiing was finally over. Now, I needed to go climbing badly. I was going crazy just going to the office and doing physics. I needed to go and do some rock climbing. And with my newfound climbing partners, I happened to be in a car driving along a very narrow road up the Val d'Orco in northern Italy. I thought I'd entered paradise because on both sides of the valley were square kilometers of unclimbed rock. Now, you must remember that where I come from in Britain, cliff climbing was a well-developed sport, and almost every square foot of rock or square meter of rock had been climbed. So unclimbed rock was at a premium and was generally kept a closely guarded secret until the discoverer had climbed every route he or she could manage. Now, to find such an expansive virgin rock was unheard of. And so I was aching to set up as many routes as I could possibly manage with my Italian friends. And as we drove up the valley, we passed a big boulder about 6 or 7 meters high. there's with a gently overhanging face. So there's the boulder on the right. And in the next slide, there's somebody, not me, but somebody actually climbing the boulder, the gently overhanging face. Now, there's a thin crack splitting the boulder, and when I saw this in the car, I yelled in my best Italian, stopped the car and jumped out, put on my climbing shoes and managed to get up the crack, which is now actually known as the fessura KOSTERLITZ. Now, I didn't find it especially difficult, but my climbing partners couldn't repeat the route. And as a matter of fact, according to what I've been told, it took 10 years till it was repeated. But of course, by now, it's been climbed hundreds of times, and the rock is actually an important feature of the little village in the valley of Cerasoli. At one time, the road was straightened, and the rock was supposed to be blown up. But the Italian climbing world in that part of Italy wanted to keep the rock because of this crack going up it, this so-called fessura KOSTERLITZ. And so actually the rock stayed and the road was diverted round it. And so, one February, some time ago, I was invited by the mayor of the little village of Cerasoli and the regional climbing community for a get-together in the village. And I was feasted and made an honorary citizen of the village. I was also told, rather to my surprise, that because of me and my rock, the tourism of the village has been booming ever since. Because apparently people came from various parts of the world to try the luck at this crack and spent money in the area. Now, I was so thanked for that. It really felt like getting a Nobel Prize again, but this time in rock climbing. Now, so let me, sorry, that was right. Now, let me get back to my path, my random walk through physics. Now, my fellow postdoc and I wrote a single paper on the vertex function, these so-called dual resonance models, or string theory, which apparently is still quoted in the literature. Now, the obvious place to go after Torino was CERN in Geneva, because the physics is very good at CERN, and for me, the mountains are close by and excellent. So both my colleague and I sent in applications to CERN. He was accepted, but in my usual disorganized fashion, my application was late. And I got the reply, sorry, all the desk space is gone. Please apply again next year. This was a bit of a catastrophe because I now faced unemployment. However, my girlfriend, Berit, just looked at me and, muttering something very uncomplimentary, walked down to the railway station. The railway station was over a kilometre from our apartment. And she walked all the way down to the railway station and bought an English newspaper with academic job advertisements. Now remember, this was before the time of the internet and so on. So long ago that half of you probably don't remember those early days. Now, when Berit got back, she sat me down at the kitchen table, opened the newspaper at the academic job adverts, and said, apply. So I did. I found 3 positions and was offered all 3 positions, and so eventually accepted a 3-year postdoc position in the Department of Mathematical Physics at Birmingham University, and very reluctantly signed the contract. Shortly afterwards, I got a letter from CERN saying that they'd changed their mind, that they would have 2 people per office instead of 1. So I could go to CERN. I immediately said to Berit that I would renege on Birmingham and go to CERN to have fun in the mountains, which was what I wanted to do from the very beginning. Both my girlfriend and my father were of the opinion that having signed a contract, I was committed to go to Birmingham, that large industrial city in the flat middle of England without a mountain in sight. And this was the last place I wanted to be. However, in the end, Birmingham turned out to be quite a nice city to live in, despite the terrible unemployment at the time. Because of, I don't know if any of you remember that time of the early 1970s when all the car factories in Britain closed, and so there was massive unemployment. The university at Birmingham was quite good. The so-called Cadbury estate was a nice place to live and to bring up a family, and we made many friends. So actually my first real job was in the Department of Mathematical Physics in Birmingham, first as a research fellow, then as a lecturer, senior lecturer, and finally as a reader. Now, in hindsight, it turns out that professionally, Birmingham University was actually the best choice I could have made, although at first it was hard to believe that this was the case. In the first year or 2, I continued my long calculations in high-energy physics, which actually didn't really go anywhere. Now, I was on track with writing up my results several times, but I was repeatedly thwarted by a group at Berkeley, which published exactly what I was doing, but they published first. Now, as I mentioned earlier, I was actually quite good at rock climbing and generally climbing mountains. So I began to seriously consider giving up physics to become a professional mountaineer. But fortunately, Berit, as I said, she was then my girlfriend, but is now my wife for over 50 years, vetoed this idea. And as an aside, a few years later, I came down with a neurological condition called multiple sclerosis, which affected my balance and destroyed any climbing conditions I might have had. And so I had to make do with my day job as a physicist and teacher, which does not require the same sort of athletic ability as being a professional mountaineer. Now, of course, I was very upset with the group, with this Berkeley group, who had, were doing exactly what I was trying to do, but always managed to publish before me. And so I descended upon my colleagues at Birmingham, asking if they might have a problem that maybe I could look at. The general answer was, sorry, no. But I was lucky in that David Fowler's suggested a problem. Fowler's was interested in a class of unsolved problems in 2 dimensions, such as the onset of superfluidity and superconductivity in very thin films. Now, he showed me this picture. and this was published way back in 1972. And what this picture is the experiment involved a thin film of helium-4 absorbed on the surface of a resonant crystal. And so they measured the resonant frequency as a function of the coverage of helium on the film. And so now classically you'd expect a very thin film of helium absorbed on the surface of a crystal that, basically you can think of it as atom by atom of helium absorbed on the surface of the crystal. And so naively, you would expect that all that would happen was these extra helium atoms would stick to the crystal, and as the crystal shakes, vibrates, the only effect of these extra atoms would be to increase the mass of the resonating body, and therefore decrease the resonant frequency. And actually, in this graph, the solid straight line is the expected decrease of the resonant frequency, that's the vertical axis, versus the coverage of helium. You would expect that the resonant frequency would follow the solid straight line. However, the experiment done in 1972 measured this resonant frequency as a function of the coverage, and for small coverages, yes, it followed the straight line, exactly as one would expect. But then suddenly, the experimental points break away from the expected straight line. And so what David Fowler said was, look, the problem here is to explain the discrepancy between the solid line and the experimental points. Because the simplest explanation for this discrepancy is that some of the helium has gone superfluid, or at least has decoupled from you've got the crystal vibrating, you've got this film of helium on top, and for some reason, the crystal is simply vibrating, and most of the helium is simply ignoring the crystal. So that there's this discrepancy between the expected resonant frequency and the actual resonant frequency. And so Thoules's problem was, he said, look, why don't you try to explain this? So I sort of looked at him and said, yeah. See, I didn't really know what he was talking about at the time. Just remember, I'd been a high-energy physicist who didn't know that much about condensed matter physics. So then when we were talking about the problem, I think the word topology appeared somewhere. And I did find Thoules's ideas very difficult and challenging, but they did make sense to me. And in fact, Birmingham University, which was, again, the place I really did not want to be, was where I learned what physics is really all about. I was working with one of the great minds in physics. And together, we solved one of the remaining puzzles in two-dimensional phase transitions, for which I got my quarter Nobel Prize. And I realized that physics is something I could devote my life to. We discussed the problem further and wrote up a couple of papers which solved a long-standing problem of two-dimensional phase transitions. Now remember, that in the system, in a two-dimensional system, which this helium film, it was how thick, maybe 2, 3, 4 atomic layers thick at most, which can be regarded essentially as two-dimensional. Now, there was some pretty rigorous theory about such systems, and this rigorous theory made the statement that in such a system, there can be no long-range order. Okay, you may ask yourself, what does that mean? Well, in general, if the difference between a low temperature phase and a high temperature phase of almost anything is that the difference between the high temperature phase and the low temperature phase is that at low temperatures there is what is called long range order. But there was a rigorous theorem that said in the system of interest, long range order didn't exist at any if the temperature is finite, long range order simply did not exist, which then implied that there couldn't be a phase transitions, and therefore superfluidity could not happen. But this experimental data here said, look, something's happening. The discrepancy between the expected theoretical curve and the experimental measurement is saying that some of the helium is decoupled from the crystal. And the simplest explanation for this is that some of the helium has become superfluid and therefore is flowing independently of the substrate. But again, existing theory said that this is not possible. And so there's this major conflict between experiment and theory and existing theory. And this was the problem which David Fowler's posed to me. He basically said, explain this discrepancy. So I went away to my little office and read papers, thought more about it, and eventually plucked up the nerve to go and back to Fowler's and discuss what my thoughts with him. To my surprise, he took my thoughts seriously. And basically we concluded that if we think very hard about the problem and said the following: suppose that, suppose we write down a theory in which the helium film is superfluid, and we could then turn the question on its head and say, okay, what excitations can destroy the superfluidity and make the fluid act normal, like a normal fluid, and the viscous, and therefore will couple to the substrate. And now the only excitation in the superfluid which can do this are these so-called vortices, where the fluid is going round and round some center, like water running down. When you pull the plug out of the bath, the water drains down the plug hole and swirls round and round. And what you're looking at then, that's a vortex. Now, vortices are the elementary excitations in a superfluid film. And these excitations are the only excitations which can destroy superfluidity. You see, you can have all sorts of local excitations, but they do nothing. They can't destroy the superfluid flow. the only excitations that can destroy superfluidity are these vortices. Now, so then the problem reduced, if you take this way of thinking seriously, the problem then reduces to the problem of a collection of interacting vortices. So you'd have the total vorticity of the whole system had to be zero. Because, I mean, if, non-zero meant the whole fluid is going round and round. That has basically infinite energy, and that its probability is vanishingly small. But you can have, say, positive vortices and negative vortices, which correspond to circulation in opposite directions. And you can have a collection of these, and they have finite energy. And therefore, they will have some finite probability according to the rules of statistical mechanics. And so the problem reduced to that of a Coulomb gas, a collection of positive and negative charges interacting with the Coulomb interaction in 2 dimensions, a logarithmic interaction. So the problem reduced to that of a 2-dimensional Coulomb gas, which is, you may say to yourself, it's not too hard a problem, but actually it is a hard problem. Now, Thales and I discussed this problem and managed to wrote up a couple of papers which did solve the long-standing problem of a certain class of phase transitions in 2 dimensions. And at age 30, I actually did my most important work, for which I just got my shared Nobel Prize. And the phrase, of course, that comes to mind is better late than never. So let me show you another couple of slides here. This is some papers on the subject. You see, the early papers were written in 1973 or so. And here's the description of the problem, the mathematical description of the problem. And so what we did was you said, okay, we assumed that we could describe the system in terms of a smooth variation of the phase. Remember now, the order parameter of a superfluid is a complex field, which has got a magnitude and a phase. And the velocity, the superfluid velocity, is proportional to the gradient of the phase. And so you could write the phase, theta, the phase of the order parameter theta, as a smooth part, which is just phi, and a part due to a collection of vortices. That's the so-called theta sub s, or theta sub v. And so the Hamiltonian of the system is something very simple. It's simply a half times the bare superfluid density times the integral of the square of the superfluid velocity. It's just the kinetic energy of the flow. And we can write the Hamiltonian for the system as, h over kt, as some k over 2, where k is a constant which has the bare superfluid density, rho sub s, times the square of Planck's constant divided by the square of the mass of the helium atom times kt. And so what we get is k over 2 times the integral of the gradient of grad phi squared minus pi k, the vortex-vortex interaction, which is just pi k sum NINJ, what the n's are just integers, 0 plus or minus 1 plus or minus 2, etc., times the logarithm of the separation divided by some constant, which we call a, which is essentially the radius of the vortex core. Then, of course, minus a fugacity term. Now, the vortex fugacity, this so-called y, is assumed a very small quantity, so we can use this to expand the problem in powers of y and do a perturbation expansion in powers of the so-called fugacity. Now, you do this, and you do some very series of rather tedious calculations. And I can hardly read my own writing now. And here's some so-called renormalization group flows in the space of the interaction, which we call K, and the fugacity y. The vertical axis is the fugacity, and the horizontal axis is this, if you like, this interaction constant K. And we notice that the renormalization flows fall into three different parts. The renormalization group equations, and they're just derived by saying what we're going to do is imagine we start with a vortex core size, radius a, which is an arbitrary, small arbitrary quantity, because the definition of the core size is somewhat arbitrary. And then all we do is increase the core size. We say we start with the core size A and then increase the core size to A times e to the L and integrate out all the excitations that occur between the original core size and this new core size. And these are all parameterized by this parameter L, small l. And if you do this, you can derive the two equations written in the top right-hand corner. This inverse K is proportional to temperature. And so what we get is dk to minus 1 by dl is equal to 4 pi cubed y squared plus higher order terms. And the effective fugacity also changes with the scaling according to the second equation. Now remember, we're assuming that this fugacity y is a very small quantity. All this is doing is we're saying that we're assuming that we're dealing with a very dilute system of vortices. There are not very many vortices. But these two apparently harmless-looking partial differential equations actually contain a hell of a lot of physics. He says, suppose we assume some initial values of this interaction constant K and this fugacity Y. And let's suppose they're lying in the bottom right-hand sector of this diagram. And suppose we start off somewhere up here. These are the initial physical values of the interaction and fugacity. And then we rescale, make the vortex core size bigger and bigger, and integrate out the degrees of freedom at short distances. And what happens is we end up with the same problem, but with new values of the interaction constant and the fugacity. And you see what happens is that if you start off with initial values somewhere on the, around here, as you increase this scale size, scale factor, the effective fugacity gets smaller and smaller, and this interaction constant changes somewhat as well, but the flow goes like this as you simply rescale the vortex core size. And you see, the question is, okay, you believe this C is just the integration constant. It is actually a function of the deviation from the critical temperature, little t, and the initial fugacity, and the equation's written at the top there. And so what happens is if this C is positive and you're below TC, so this little t is negative, little t is basically just the deviation, fractional deviation from the critical temperature. And we see that there's a region where the fugacity, effective fugacity flows to 0. Now, when the effective fugacity flows to 0, that means there are no vortices. So it's a system, effective system, which has no vortices. And if the system has no vortices, it's superfluid by definition. Because remember, the only excitations that can destroy superfluidity are vortices. And if there are no vortices, superfluidity cannot be destroyed. And therefore, a system that lies in this upper right-hand quadrant, this lower right-hand quadrant, represents a superfluid. If you're right at TC, your system follows this straight line, which flows down to this point here. And if you're above TC, you either, depending on your parameters, you're either in this region or this region. But in any event, as you do this rescaling, the effective fugacity, Y, eventually increases. And of course, when this fugacity increases, it's of order 1, what that means is you've got a system where you've got a lot of vortices and anti-vortices. And these excitations, which means you have a high density of vortices or anti-vortices, and this means that your fluid is normal. It's a normal dissipated fluid. In other words, so this is the picture of how you can have this superfluid transitions in 2 dimensions. Now the question is, of course, this is all very well. Can you get anything more out of it? I mean, at least what this does, it explains how there can be a transition. And of course, you can get more out of it by simply asking the question, okay, so here are some of the crucial predictions of our theory. Now, the measured stiffness, or the measured value of this interaction is call it KR, which is proportional, and this KR is proportional to the measured superfluid density. Okay, so it is, remember, it's proportional to the actual superfluid density in grams per unit area that you measure in an experiment. And so, if you look at the bottom 2 lines, you can see that this interaction constant is a combination of the measured superfluid density, this rho sub SR, with a superscript R, times Planck's constant squared divided by the mass squared of the helium atom times Boltzmann's constant temperature. This is equal to this so-called, normalized coupling constant. And what this renormalization calculation does for you, you can show that the actual value of this measured superfluid density, which depends on the input interaction parameter K0 Y0, and then this is equal to the same quantity as a function of the same interaction constants but measured at L equals infinity, normalized. But if you're below Tc, this y of L equals infinity is 0. Remember? The fugacity is scaled to 0. And it's not hard to show that this quantity is just 2 over pi plus some constant times the square root of Tc minus T. And so if you like, you can then say that if you suppose you're just below the onset temperature, just below, then the actual measured superfluid density in mass per unit area, just below the critical temperature, divided by the critical temperature, is this combination of fundamental constants. Twice the square of the mass of the helium atom times Boltzmann's constant divided by pi times Planck's constant squared. And this is essentially 3.5 times, sorry, that should be 10 to the minus 9, I beg your pardon, that's an error, grams per square centimeter per degree Kelvin. Now that is the essential prediction of a theory. And there is no way that this prediction can be changed. It doesn't matter what you do with with your system. You can fiddle about with the system as much as you like. This prediction, you cannot change it. You're stuck with this. And so the theory stands or falls with a measurement of the ratio between the measured superfluid density divided by the onset temperature. Now, fortunately, the experiment was done. And it was really done by David Bishop and John Reppy in 1970. Well, it was actually done in 1977, but it was published in 1978. Vertical axis is the measured superfluid density times 10 to the 9, not 10 to the 8, in grams per square centimeter, versus the critical temperature. You may ask yourself, look, how can you vary a critical temperature? So critical temperature is normally, you have your system and you make a measurement and no matter what you do, a given system has a given critical temperature. So how can you vary it? That's easy. You just make the helium film a little bit thicker, then you will increase the critical temperature. So this makes perfect sense. You can change the onset temperature easily by just changing the thickness of the film, which just means you're looking at a film in equilibrium with helium gas. Some of the helium's adsorbed, and you want more helium on your substrate. Just crank up the pressure, external pressure of the helium gas. And so then there's a set of different experiments you can do. And in particular, you can do, say, third sound experiments. And there's a collection of experimental points. That's these various points which are on this graph here. And I remember being told that Bishop and Reppy were staring at they had plotted all these experimental points on this, in terms of the measured superfluid density versus the critical temperature, and they got this mass of points. And they were wondering what to do with it. Then somebody came along and said, look, these guys in Britain, KOSTERLITZ and Thalers, they've actually got a prediction. And their prediction is that this superfluid density in 2 dimensions versus the critical temperature follows a straight line. So there's a straight line. And remember, this straight line, the theoretical prediction is the solid line there. There are no adjustable parameters. That prediction, that is the theoretical prediction. There's no way of changing it. And if you look at that graph, you'd think, well, it's not a bad fit. I mean, after all, the experimental points are sort of all, seem to be scattered about the straight line pretty well. And so, being somewhat biased, I would say that that is confirmation, experimental confirmation of the theory. So then perhaps we should look at one more. Now you can do a similar sort of comparison with theory and experiment for the melting of a 2-dimensional crystal. Because the excitation, the assumption you make, you have a 2-dimensional system and you say, okay, it forms a crystal. And then you say to yourself, what sort of excitations can screw up the crystal structure? And the answer is dislocations. And so one can make up a theory of interacting dislocations in 2 dimensions. It's a little more complicated than the superfluid theory, but it can be done fairly easily. And so then, here's the experimental data. You can plot an appropriate combination of elastic constants. Because in a 2-dimensional isotropic solid, which it is an isotropic solid because the isotropic solid in 2 dimensions is a triangular lattice, and that's the natural lattice that a 2-dimensional system will form. And so there's a bunch of elastic, if you take the combination of elastic constants, which forms the so-called Young's modulus, and you plot this against the inverse temperature, you get this bunch of experimental points. You see, you got rather large error bars, yes, but then you say, okay, we have this theoretical prediction about when this 2-dimensional solid crystal will melt. And the description is in terms of the excitations, these dislocation excitations, which play the role the same role as vortices do in a superfluid. And so one can, it's a more complicated system than the superfluid system, but Halpern and Nelson have done all the calculations. And the theoretical predictions are this red curve here. And the value of the Young's modulus at melting is precisely here. Okay? And the error bars are rather large, but the agreement between theory and experiment is not bad. And so one would regard this picture as confirmation of this defect-mediated melting theory in 2 dimensions. There's another system which one can describe in terms of defect-mediated theory, and this is okay, so let me just show you the last slide. And so the concluding remarks are, I'd like to thank David Thowles. Unfortunately, David Thowles died a few years ago, which is a great shame because Thowles was definitely one of the great geniuses in theoretical physics. I'd put him on a par with people like Richard Feynman, Julian Schwinger, and so on and so forth. And so I thank David Thowles for introducing me to this beautiful problem, David Nelson for collaboration and discussions, John Reppy for many useful discussions, and of course the Nobel Committee for the recognition. And I would like to thank my wife, Berit, for an incredible journey taking us from Oxford to Torino to Birmingham to Providence, and Karen. And finally, but not least, my children, Karen, Jonathan, and Elizabeth, for putting up with a rather strange father and his very strange pursuits. And thank you for your attention.
Well, we thank Professor KOSTERLITZ for sharing with us his really, I would say, not strange, but in fact wonderful life journey. So we have time for a couple of questions. Yes, Penka. Yeah.
So I understand that I'm particularly interested you were talking about.
Sorry, my hearing is very bad.
Okay. So you were talking about a theory of a transition, say, from super fluid state to a normal state by exciting of vertices. But the theory is two-dimensional. So I just wonder, do we know anything about the three-dimensional system? Or are there any difficulty in theoretical in extended from 2D to 3D?
Well, of course, if you think about a three-dimensional superfluid, of course, the sort of excitations that will destroy the superfluidity will be similar. But the point is that in 3 dimensions, the vortices are a little bit more complicated. They can form rings and so on and so forth, whereas in 2 dimensions, the vortices we're talking about are perpendicular to the layer, and therefore it can be regarded as points. In 3 dimensions, you've got these possibly vortex rings and vortex lines, etc. And so life is much more complicated. One can construct a theory, a vortex theory of superfluidity there in 3 dimensions. And this was done by, what's that guy in Norway called? Asli Sudbo. And he did some extensive computer simulations, you know, on the vortex theory in 3 dimensions, and got pretty good agreement with the standard theory. So it seems that it can be worked out, but it's much more complicated than in 2 dimensions.
Okay, it's been verified experimentally?
I'm sorry?
It's been, any experiment verified the 3D simulation or whatever? Are there any experiment to do it?
Most of the experiments originally were done in 3 dimensions, of course, because doing a superfluid experiment in 2 dimensions is pretty difficult, as you can imagine. And so, of course, the experiments in 3 dimensions, the measurements show that the superfluid density vanishes at the transition, whereas in 2 dimensions, it actually jumps this same quantity jumps discontinuously to 0 at the transition. So, you know, as you approach the transition from below, the superfluid density decreases and then reaches a certain value. And then as you lower the temperature slightly, the superfluid density just vanishes discontinuously. But the transition is still continuous. It's not a first-order transition.
Thank you.
Yes.
Thank you for the talk. I have some questions about your earlier research career. You once said that at 1970s, like it wasn't a good time for finding a job, and you met some problems also at that moment.
I'm sorry.
You once said like in 1970s, like it's not a good time for finding job. It's like and you also had some maybe difficult time, like you went to Birmingham, but you didn't think it's the best place for you. So
yeah.
So I was just curious, like at that moment, what is the most important factor or motivation for you to keep choosing physics and doing research during that period?
Well, yeah, I really enjoyed physics because, you know, it was one of the few intellectual subjects that I was able to do because, you know, as I said, I had this awful memory. I can't remember more than, you know, I like to say that I can remember a maximum of 10 facts, but I'm not too sure about the last 4. And so anything that I can't do with the 6 facts I'm sure of is too hard for me. Mm-hmm. You know, so I had to struggle with this bad memory. You know, the various other things, of course, but, you know, but you're same with everybody. Everybody has some misfortune and so on and so forth. But in my case, things worked out okay. I was lucky. My parents, fortunately, my father in particular always said, "You do what you want to do. Never, it doesn't matter what you do as long as you enjoy it." And you know, I would offer the same advice to any students. Find something you enjoy, you're good at, and you enjoy, and have fun with it. And so I had a lot of fun with physics, and as I say, things worked out for me. I'm not saying it's going to work out for everybody, but to me, one of the most important things in life is to enjoy yourself. You know, if you're not having fun doing something, it's not worth doing. So, I mean, I'm sure everyone will find something you like doing.
Yeah, because I remember you said at some point you once trying to be a mountaineer, right? So during that period, so
Okay. In my younger days, I was actually pretty good at it. And I loved doing it. You know, I liked the risk. You know, there's nothing to compare with going out, you know, in the unknown, on a steep cliff, knowing that a mistake could have serious consequences up to and including death. Death. And if you like that sort of thing, it's very addictive, very addictive. And so at one stage of my life, I thought, I'd like to do this the rest of my life very much. But then I got a neurological problem, which meant I had to quit climbing. So fortunately, I had a day job, which I enjoyed too. So I stuck with my day job.
okay, thanks. Yeah.
Yes, Kambil, yeah.
Well, thank you for your interesting story. So I wonder, your background in high energy theory help you, in transiting into condensed matter physics.
Yeah, but of course, my background in high energy theory is a bit old, because it was all before the days of gauge theories. And so, you know, it's rather primitive. And I never found anything in high energy theory that turned me on like this problem in condensed matter. You know, the problem of phase transitions really fascinated me, and so I could really, you know, work hard on that. In high energy, I never found anything comparable. I mean, now, of course, high energy physics is getting quite interesting, but you know, the way things seem to be going, you know, the theories seem to be falling apart, and it looks like one's going to have to go back to the drawing board. But that's the fun of physics, you know. You've got to be prepared to, you know, if something doesn't work, throw everything away and start over. And, okay, if you like that sort of thing, that's fine. But, you know, for me, with high energy physics, I didn't find anything that really excited me.
Yes.
Thanks, Professor, for the nice talk and your life journey. I am in the final year of PhD, and I just submitted my PhD thesis, and I am yet to defend. I want to tell a little bit about myself. When I started PhD, I work in the ultra cold dipolar atom system. So we have been, our group, like Professor Gung Jo is working on the dipolar Bose-Einstein condensate. Recently we published one paper in the Science Advances on BKT transition in dipolar atoms. So here is few words about myself. Is when I started my PhD, I wanted to do both theory and experiments. So I keep up my research projects. I do experiments and I find the theoretical explanation for this. So I solve the Gross-Pitarski equation. So at the end of the day, I have a question. Like sometimes I doubt because I worked in the experimental group where people are very good, smart in experiments, and I had fewer chances to discuss my theory with my colleagues. So my question to you is it a good decision to do both, or should I focus on only one theory, or only experiments? Or should I continue both in both?
Well, I mean, it's clear that in physics, both theory and experiment are very important, and one complements the other. But an individual person, there are very few people who can do, are both good experimentalists and good theorists. So really one has to choose. Or almost everybody has to make a choice between theory and experiment, because it's almost impossible to be able to do both at the same time. So you have to pick one. I mean, for me, the choice was simple, in that I was a walking disaster in an experimental lab. So, basically, all I had to do was walk into a lab and things would stop working. And so, to me, the choice was simple. It was either theory or nothing. Maybe you're lucky. Maybe you can do both. Then you're just going to have to pick which one you enjoy most, more than the other.
Yeah, I find like
Little choice.
when I do experiment, then I have forgotten the theory I did. So then again to recap, it takes a week or 2 weeks, and then I have to waste time there. And then when I go to do experiments, then I think like my theory is not matching because I'm learning. I'm not expert in any of the fields. So I really find it difficult to pursue both. So.
Well, for example, with what I was talking about, it started off as a purely theoretical exercise. When we started it, there was no real experiment available, except some rather crude sort of experiments, where you had this. The question was, to start with, was how can there be superfluidity in 2 dimensions? Because existing theory said this was impossible. But then there was an experiment which said, look, it's obvious. Here is the transition. It's obvious that there is a transition in 2 dimensions. Making it quantitative, however, that was a different matter. And the question, if you're trying to ask what should I measure experimentally, you could say, well, what do you want to do with the measurement? Do you want to demonstrate what you want to demonstrate here? Do you want to demonstrate something just quantitative, or do you want to do something quantitative? And of course, making a quantitative prediction theoretically is extremely difficult.
Yes, I agree.
Because there's so many factors which can affect your prediction. However, in this particular case, one can actually show quite very convincingly that the quantity I wrote down, you cannot change that prediction. No matter what you do to the theory, you come up with the same answer. Now, this may seem a very strange statement to make, but it relies on the standard normalization arguments, relevant variables, irrelevant variables, all this sort of wonderful jargon that Ken Wilson introduced us to. But one can almost make a rigorous proof, well, not rigorous, but one can make a very convincing case that this particular combination of measurable quantities has to have this value at the transition. And no matter what you do to the theory or to the system, you can't change that number. You can change the critical temperature, you can change the superfluid density, sure, but if you take the ratio of the two, it has to be that number. And so that's a smoking gun prediction. You know, the theory either stands or falls with, you know, that if you make an experimental measurement of that number, if it doesn't agree, your theory is wrong, and you have to go back to the drawing board. It's an amazing prediction, and it's amazing that experimentally it worked out. You know, we certainly didn't expect it, but you know, it's wonderful that it did. And it's also amazing that such a prediction, you could make such a prediction. Because you know, such predictions are rather, there are some in the literature, but very few. Yeah, I mean, you asked the question, how many exact, unchangeable predictions are there in physics? And the answer is not many. But this is one of them. And you know, and it's pretty amazing that, you know, it's very pleasing that we were able to come up with it, such a prediction, and even more pleasing that it agrees with experiment.
Thank you very much for explanation, Professor.
Mike?
Thank you. It's nice to see you again. It's a more mundane question. I'm curious why you left Birmingham and moved to Brown.
My hearing's absolutely terrible.
I'm curious why you left Birmingham and moved to Providence.
The reason I left Birmingham was because Thowles left Birmingham for the States, and Birmingham had offered me a research professorship with you know, a bit of funding and so on. So I thought, might be good to stay. But then, about 2 days before this was due to start, Margaret Thatcher, you know, removed the money, so it was taken away. So I thought, screw you, I'm going to Brown. I'm going to take up this offer from Brown University. So I left. Yeah, I got really annoyed.
So they reneged on you.
Sorry?
They reneged on you. They had a contract they canceled with you.
Yeah.
Okay, thank you.
You mentioned Ken Wilson in your previous answer to a question. I was just wondering, at the time when you were doing this work, did you have, how closely were you paying attention to Ken Wilson's work on renormalization group?
Not so much, because I learned my renormalization group stuff from a paper by Anderson and Yuval, who did this, called it poor man's scaling, I think. And I managed to modify what they'd done to be able to treat the two-dimensional theory of interacting vortices. And I was very pleased that, you know, I could actually do it and, you know, come up with similar results to what Anderson and Yuval had derived for this long-range 1/r² Ising system. You know, as I say, that's where I learned the renormalization group from, although at the time I didn't know it was a renormalization group. Because, you know, basically, when David Thowles sort of suggested this problem to me, threw a load of papers at me, and Anderson and Yuval were one of the papers, which I sort of read and tried to understand what was going on. I think I did nothing for about 6 months except read and reread that paper, trying to figure out what they were doing. And that was, basically that's how I learned a normalization group.
Thank you.
So are there other questions? Okay, if not, let us thank Professor KOSTERLITZ again. So today it is indeed wonderful that you tell us that you have climbed rocks that no one climbed before, and you have solved problems that no one have solved before, and therefore you get the Nobel Prize. But I guess for our, next generation here, I have to recognize that the fact that not everyone can climb, big rocks, and not everyone can solve a problem to get a Nobel Prize. But at least hope that today's talk inspire us that with determination and concentration, and then we can probably solve problems, and we should try to find problems that no one else have solved before. I think that is what makes life interesting, right? So with that, let's thank Professor KOSTERLITZ and hope that you can come again in the future. Okay.